grade 11s. This is physical science. My name is Gillian, and we are looking at friction. Now, a true test of our mettle and our understanding is to try out questions. So that's what we're going to do today. And you will notice as you start practicing these questions that they are all involved in the vector and a vector section in Newton's laws, and the friction questions are they're couched in those questions. So we do need to have quite a good knowledge of forces and how they act and how we draw them. So let's dive in and look at this first question. So a constant force F pulls a 50 kilogram block. Here's our block over here, 50 kilograms. Ooh, at constant speed, constant speed. What does that mean? Well, that means that acceleration is equal to 0, doesn't it? Constant speed, velocity is constant. It means there's no acceleration. Over a rough horizontal surface. So that's telling us, the word rough is telling us that there is going to be friction involved in this. At some stage, they will ask us about friction. And they've labeled the surface AB. They've even drawn it like this, so we can see that there's going to be friction, as shown in the diagram below. Okay, then they give us the coefficient. The coefficient of kinetic friction is mu k between the block and the surface. Okay, so the block and the surface, okay, we know that, and then they give us this value, 0.4. Now, when they give us these kind of questions, they normally lead us into answering the calculations. So they will either give us a drawing, we've got to draw a free body diagram or a force diagram, or they'll ask us definitions related to Newton's laws. So let's see what they ask. Draw a labeled, they've given us a clue, labeled free body diagram showing all the forces acting on the block. Okay, so free body diagram, that's a diagram where you draw a dot for the object, and then from that dot, all the other forces go from that dot out, and they have to touch that dot. Okay, so let's have a look at this picture and see what forces could be acting on it. So we do have a mass here, and so if we've got a mass, we know that we're going to have a gravitational force. Okay, so Fg. Okay, we know about that. We know we've got F, so F's at an angle. Here's F. Right, what about a normal force? So the normal force is between the surface and the object. So if N, or some of you write it as a big N. And then they've told us that there's a rough surface, so there must be a frictional force. Okay, so like that. Right, so let's put that. I don't think we've left anything out. That looks good. So we're now going to put that into our free body diagram. So we're going to draw the dot. Come and draw it quite big so that you can see it. So there's the dot, there's the object. Okay, it has got a force of gravity, Fg, and we know that that is equal to ma. Huh? All right. Now, what about our normal force? There it goes, or N. Our frictional force is working in the opposite to the direction of movement. So we're assuming that this is being pulled, it's being pulled in that direction, and so the force is going to act opposite to that of movement, and so that is going to be our frictional force. We can write it like this, and we're going to put a little k next to it. That means that it is kinetic frictional force. Now, this force F, the applied force, is at an angle. So we're going to draw it at an angle, and we're going to call it F. All right, I think that's everything we need. Yes, so let's move on. State Newton's first law of motion in words. Now, often when they ask you to state a law, it means they're leading you on to answering the more difficult questions. They're giving you a clue, really. So what is Newton's first law of motion? So his first law of motion is talking about a body which is at rest, in a state of rest, or in a state of constant motion. And he says there that a body will remain, so let's write that, so it is going to remain at, or let's write in, a state of rest or in constant motion, constant meaning the same, there is no acceleration, constant motion, motion, or velocity, we could say velocity. Unless what? Well, unless there's going to be a net force acting on that body. So we're going to write that. So unless a non-zero resultant, or you can write the word net force acts on that body. Okay, that is straightforward learning, you just need to learn it. Now they ask us, calculate the magnitude of the force. So here's F here, we need to calculate that magnitude. Now there are lots of things going on in this particular situation. And so we need to be pretty careful about what is happening. So let's start with looking at this, this big applied force F and the motion, the movement of this object. So if the object is moving in this direction, then the component of the force that is going to help with the movement is going to be the vertical component. So I'm going to draw on this picture and I would encourage you to do so as well on your exam paper or your test paper. So we see that this force has got two components, a vertical component, and it also has got a, sorry, I've made a mistake there. Let's erase that. What's that? It's not vertical. Of course it's not vertical. It is the horizontal component because it is parallel to the ground, and here is the vertical component. So it is the horizontal component that applied that gives us the motion. So have a look at that. So that's quite an interesting thing. So we can write relationships for finding the value of these two components. I'm just going to jot them down here. So we've got the horizontal component is going to be the adjacent side to that angle. And so we are going to say if cos theta, which happens to be 20 degrees. What about the vertical component? Well, the vertical component is opposite the 20 degrees. It's the opposite side. And so the vertical component is going to be force sine theta, which is 20 degrees. Okay. We are sitting with a lot of unknowns here. There are a lot of unknowns. So we're going to have to look at something different to try and help us to calculate force. So this object is moving. So Newton's laws tells us that F net is equal to ma. So we know that. We also know that acceleration is equal to 0. We know this because they've told us it's moving at constant velocity or constant speed. It means the acceleration is 0. So we can then automatically say that F net is equal to 0. But what are the forces that are acting on this object over here, this 50 kilograms? We have got a frictional force, it's a kinetic frictional force, and we have got this component, this horizontal component, which is giving us the motion. So what is the net force going to be then on this object? It is going to be the horizontal component. There we go, horizontal component. What? Subtract the frictional force, and it's a kinetic frictional force. It's equal to 0. We've already figured out what this one is. We've worked it out. We've said that the horizontal component is the force that we're trying to find. That's what they're asking for, cos of the angle, which is 20 degrees, subtract the frictional force, the kinetic frictional force. Now, what do we know about the frictional force? We know that the frictional force is equal to mu k times by the normal. Do we have mu? Yes. They've given it to us. I think they gave it to us, let me look back. I think they gave it to us as 0.4. Oh, there we go, 0.4. Okay, they've told us already it's 0.4. Do we have the normal force? No, we do not. So this is the tricky bit. So now we've got to figure out what is the normal force. I'm just going to rewrite our thinking out. So this is F, the force, cos 20 degrees, minus mu k times by the normal force equals 0. So now we've got to figure out what is going on. How are we going to sort out the normal force? So, because this object is being dragged up, there is a component which we've already drawn, which is this component here. It is the vertical component of force, of the force F. Because that is adding to our situation, remember we're not lifting this, it's being dragged, but it's being dragged at an angle. That vertical component is going to play a part in the normal force. And so it's going to have a bearing on the normal force. So we can say here, remember our normal force is related to our gravitational force, okay, normal force. That's our normal. But we find that there is a vertical component to it. The vertical components of the force and the normal force are working in the same direction. The gravitational force is in the opposite direction. So what can we say about this? I'm going to change my pen color because I want us to really see this. So we've got our gravitational force, and that is equal to the normal force plus the vertical force, because they are both acting in the same direction. Okay, there we've got our normal force. We can calculate that, okay, or we can get an equation to help us calculate that. So let's go with this. So a gravitational force is going to equal 50 times 9.8. We know that it's mg, right? Normal force is what we've got to try and find. What about this vertical component? We've already written it down. We've seen that the vertical component is F sine theta, which is 20 degrees. We can write an expression then for the normal force. It's Fn, and that is going to be, if we work it out in our calculator, it's 490 minus 0.34 F. There's our expression. What are we going to do now? We are going to put this into our original thinking around finding the force F. So let's substitute it in, and we're going to get this. Force cos 20 degrees. We're almost there. Minus. Now, we've got our mu k, which is 0.4, they've told us, okay, times by normal force, which is this expression, 490 minus 0.34 F. It's equal to 0. Okay, now we can work with it. We're going to use our mathematics and our calculators, and we're going to come up with the following. I'm going to write it out quickly for you. I have got it here. It is 0.94 F. Okay, so that's this one here. Plus 0.136 F minus 196 equals 0. I'm going to move up to this side here. I'm running out of space. And so we get F is equal to 196 divided by 1,076. And my answer then is force is equal to 182,156. Oh, squeeze it in, newtons. And this is going to be 20 degrees from the horizontal. Sure, grade 11s, that was hectic. We have to take a break now, and I will see you after the break. Welcome back, grade 11s. Phew, that was mammoth. So now we're going to just take a deep breath, and we're going to carry on with the rest of this question. So it says here, calculate the magnitude of the normal force. Well, we found out what the expression is for the normal force, and this is what it was. We found out that it was, so the normal force is equal to 490 minus 0.34 F. Now this is easy because we've discovered what F is. That first question, that mammoth question, was discovering what F was. We found out that it was 182, what was it, 156 Newton. Okay, so we're just going to substitute in now 0.34, and we substitute in that value, which is 182,156. Sorry, I'm squashed up here a little bit. Let me move over. And so that is going to give us an answer, once we've used our calculator, of 428,067 Newton. Fantastic. We know which way the normal is, so we could leave it, leave the direction, okay? Next question. Calculate the magnitude of the frictional force, okay, the frictional force. So this is also pretty easy for us because our frictional force, we know what that is. So it's a kinetic frictional force, and that is equal to the coefficient of frictional force times by the normal force. Now we've already discovered what the normal force is. We've just been asked to calculate that. And so all we're going to do is we're going to substitute in our mu value was given to us as 0.4, and we're going to times it by this value that we have just calculated, 428,067 newtons. Okay, we pop that into the calculator, and we get an answer of 171,227 newtons. Excellent. We want to say the direction of this. It is going to be opposite to motion. Okay, very important. Okay, what now? They give us another question. The same constant, force, F, is applied to the block over the same rough horizontal surface as before, but the direction has changed. Sorry, not directions, direction has changed. You can see here, look there. Now it is a pushing force. It is not a pulling force. They are asking us to give us a reason why the block will move slower than before. This is interesting. So if we look here, we can see, if we break it up, we can see that we've got a vertical component which is in the downward direction, and the horizontal component is the same as before. There we go, it's the horizontal component. I'm going to change my pen. I want to show you the other one. So with the other one, it was up like that. And what did we have? We had the horizontal component, which looks the same, or looks similar. And we had a vertical component. Have a look at the directions. Can you see that in the first one, the vertical component was up, and in the second question here, or the second situation when the force is acting in this direction into the block, pushing it rather than pulling it, we've got a downward component. The vertical component is acting down. What does that mean? It means that we have got a normal force in this situation, which is going to be the force of gravity plus the vertical component. Why? Well, because our downward force is the same as the upward force, so the normal force, but in the opposite direction. So what is making up this downward component? It is or downward force. It is the force of gravity plus this vertical component which is added. Okay, because it's acting in the downward direction. So our normal force is being changed. So we need to say that the normal force is increasing. What does that mean? Well, if the normal force is changing, it means that the frictional force is going to be changing. So, therefore, the frictional force is also going to increase. What does that mean? That means it's going to be very difficult to move this block. And that is why the block is going to move slower. Grade 11s, let's see if we have time to tackle this problem. We don't have lots of time, but we can do parts of it. So this problem is two blocks put together. You can see it on the screen. There's an 8 kilogram block. You can see it's on a horizontal surface, and the 4 kilogram block is on a slope. Okay. They tell us there that it is joined by an inelastic string of negligible mass. That just means it's not going to have any effect on what we're trying to work out. It runs over a frictionless pulley over there. The 8 kilogram is on a horizontal surface. The 4 kilogram is on an inclined plane. You can see here it's 40 degrees. And there is a coefficient of friction, and they tell us that it is for both blocks, and it is at 0.2. And it tells us that this block accelerates. It is accelerating. Okay, so there is an acceleration. What are they asking us to do? State Newton's second law of motion in words. I'm sure by now you know that. So I'm not going to go through that, but that is going to give us an indication of where they're going, right? With the questions that they're going to ask us. When they talk about in words, they don't want the formula. So we know that the formula is F net equals ma. They don't want that. They want you to actually write it in words about the relationship between the force, the mass, and the acceleration. Okay, draw a labeled free body diagram of all the forces acting on the 4 kilogram block. So we'll do this. This is all we have time for. So here's our 4 kilogram block. There it is there. Okay. It's on a slope. What are the forces acting on it? So we're going to draw the block as a dot. Here it is here. That's my kilogram block. We know that we've got a force of gravity working on it. So there is force of gravity. Now, what else do we have? There's a string involved here, so there must be a tension force. Okay, so there is a tension force. So we're going to put the tension force there. Okay, tension force. We know that there is friction involved. How do we know that? They have told us that there is friction involved. They have given us a coefficient of kinetic friction. So we need to write that in. Now, what about that? Well, that is opposite to the direction of motion, and the direction of motion is in that direction, and so the frictional force is going to act in the opposite direction. So it's going to act up the slope or parallel to the slope, and so we need to indicate that. So our line goes from the dot, these lines can't touch, and there we go. So it goes from the dot, and that is my frictional force. I'm going to label it F, okay, because I know it's kinetic, that's kinetic friction, this object is moving. Then what about the other forces acting on this block? Well, we have a normal force, don't we? We've got a normal force which is acting perpendicular to the surface there, and it is going to be a component, it's going to equal to the perpendicular component of the gravitational force. So we're going to place that in, and so there we go, there's the normal force over there, and we're going to write Fn, or normal force. Right. Grade 11s, I hope that has helped you with how to solve these problems. There will be these questions on the MTN online school platform. Go ahead, go and look at them, practice them, and check out the answers. We will see you next time.